What if I told you that the way you perceive space and time could be fundamentally wrong? Welcome to a journey that will challenge your understanding of the universe as we delve into Albert Einstein's theories of relativity. Einstein, in his groundbreaking work, redefined our concept of space and time, combining them into a four-dimensional space-time continuum. His theories of special and general relativity, proposed in the early 20th century, have been nothing short of revolutionary, altering our perception of the universe and paving the way for modern physics. These theories have been tested and validated numerous times, especially through experiments conducted in the vast expanses of space. They've revealed how light bends due to gravity, how time can slow down, and how gravity influences the orbits of planets and satellites. But don't just take my word for it. Let's dive into the top 10 space-based tests that have proven Einstein's theories to be true. At number 10, we have the Gravity Probe A, launched in 1976. This remarkable experiment was designed to test Einstein's theory of general relativity, specifically the effect known as time dilation. Time dilation, simply put, is the idea that time can slow down or speed up, depending on how fast you move or how close you are to a gravitational field. For the Gravity Probe experiment, a hydrogen maser atomic clock, the most precise timekeeper of its era, was sent up about 6,000 miles into space. Comparing the time on the spaceborne clock with one on Earth, the experiment confirmed, with an astonishing precision of 1 part in 100 million, that time runs slower the closer you are to a massive object, just as Einstein had predicted. These results were groundbreaking, providing further proof of Einstein's theory. Gravity Probe A opened up a new vista in our understanding of time dilation. At number 9, we have the Cassini spacecraft. Launched in the late 20th century, the Cassini spacecraft was not just an explorer of Saturn and its moons, but also a cosmic laboratory to test Einstein's theories. One of the most crucial tests involved measuring the speed of light in a gravitational field. This was accomplished by transmitting radio signals from Cassini back to Earth. As the signals passed close to the Sun, they were slightly delayed due to the Sun's gravitational field, a phenomenon predicted by Einstein's general theory of relativity. The results were astonishingly accurate, aligning with Einstein's predictions within a hair's breadth of 1%. This test was significant because it provided a more precise confirmation of the speed of light's reduction in a gravitational field, reinforcing our understanding of general relativity and its implications on the universe's structure. The Cassini mission thus became a beacon in our quest to understand light's behavior in a gravitational field. At number 8, we have the Pound-Rebka experiment. This groundbreaking experiment, carried out by Robert Pound and Glenn Rebka in 1959, was designed to test Einstein's prediction of gravitational redshift. This phenomenal theory suggests that light loses energy as it climbs out of a gravitational field, leading to a shift towards the red end of the spectrum. Pound and Rebka ingeniously used a form of light known as gamma rays, emitted from a radioactive iron source. They compared the energy of the rays at the top and bottom of a Harvard University tower, finding a minuscule but significant difference. This was the first precise verification of gravitational redshift, a key prediction of Einstein's theory of general relativity. The results of the Pound-Rebka experiment have had a profound impact on our understanding of the universe, confirming that gravity does indeed affect light. The Pound-Rebka experiment, hence, shed light on the phenomenon of gravitational redshift. At number 7, we have the Gravity Probe B. This unique experiment was designed to test two predictions made by Einstein's theory of general relativity: the geodetic effect and the frame dragging effect. Now, you might ask, what are these effects exactly? Well, the geodetic effect refers to the warping of space and time around a gravitational body, while the frame dragging effect is the idea that a rotating body drags space-time along with it. Launched in 2004, Gravity Probe B carried ultra-precise gyroscopes to measure these effects by observing the angular changes in the direction of spin. After painstaking data analysis, the results were in. Einstein was right, once again. The measurements matched his predictions, reinforcing our understanding of how massive objects influence the fabric of space and time. So, with its successful mission, Gravity Probe B gave us a deeper insight into the frame-dragging effect. And that's why it deservedly takes our 7th spot. At number 6, we have the LIGO. The Laser Interferometer Gravitational Wave Observatory, or LIGO for short, is a remarkable piece of technology that took Einstein's predictions from paper to palpable reality. LIGO is designed to detect gravitational waves, ripples in the fabric of space-time caused by catastrophic events in the cosmos. In 2016, scientists at LIGO announced they had detected gravitational waves for the first time. This groundbreaking discovery was the result of the cataclysmic collision of two black holes, an event so powerful it sent gravitational waves rippling through space-time. The detection confirmed a major prediction of Einstein's general theory of relativity, and opened an unprecedented new window onto the cosmos. It was, in essence, a new way of seeing the universe. Through LIGO, we are now able to observe the universe's most violent phenomena, revealing secrets that have been hidden for billions of years. LIGO thus marked a major milestone in our detection of gravitational waves. At number 5, we have the Hafele-Keating experiment. This groundbreaking experiment took place in the year 1971 with the objective of testing time dilation, a concept central to Einstein's theory of relativity. The experiment involved atomic clocks flown on commercial jets around the world. One set flew eastward while the other traveled westward. The idea was to see if the moving clocks would tick slower than stationary ones, as predicted by Einstein. After the flights, the clocks were compared to a reference clock that had remained stationary. The results? Just as Einstein predicted, the traveling clock showed a slight but measurable time dilation effect. The eastward clock lost time compared to the reference clock, while the westward clock gained time. This experiment confirmed that time can indeed slow down or speed up depending on the speed of the observer, a phenomenon we now know as time dilation. The Hafele-Keating experiment revolutionized our understanding of time dilation. At number 4, we have Eddington's solar eclipse expedition. This remarkable endeavor took place in the year 1919, during a total solar eclipse. The man behind the mission, Arthur Eddington, aimed to confirm an intriguing prediction made by Einstein's theory of general relativity that gravity can bend light. Eddington's team embarked on a daring expedition to Príncipe Island and Sobral, Brazil. Their objective was to photograph stars near the sun during the eclipse. According to Einstein, the sun's massive gravitational pull would bend the stars' light, causing them to appear slightly shifted from their usual positions. The results? Eddington's photographs indeed showed the stars displaced from their expected locations. This monumental discovery confirmed Einstein's prediction, catapulting him to fame and forever changing our understanding of the universe. Eddington's expedition thus illuminated our understanding of how gravity bends light. It was a stellar affirmation of the fact that light, though seemingly untouchable, is indeed influenced by the invisible force of gravity. At number 3, we have the Shapiro time delay. This fascinating experiment was a cosmic test of Einstein's theory of general relativity, specifically looking at the speed of light in a gravitational field. The Shapiro time delay involves the delay in signal timing when a light or radio signal passes close to a massive object. This delay is due to the curvature of spacetime caused by the object's gravity. In the 1960s, Erwin Shapiro proposed this effect and later confirmed it using radar signals sent to the planets Venus and Mercury. The results? They were in remarkable agreement with Einstein's predictions, giving us a deeper understanding of how light behaves in the presence of gravity. So what's the big deal? Well, this finding is significant because it provides yet another confirmation of general relativity and also has practical applications in fields like satellite navigation. The Shapiro time delay, hence, added a new dimension to our understanding of light's speed in a gravitational field. At number 2, we have the Perihelion precession of Mercury. This is a fascinating phenomenon where the orbit of Mercury, the closest planet to the Sun, shifts over time because of the effects of gravity. This shift, or precession, is more significant than what classical physics would predict. Now, why is this important? Well, it was one of the first tests of Einstein's theory of general relativity. According to this theory, massive objects like the Sun cause a distortion in the fabric of space and time around them. This distortion affects the orbit of nearby objects, like Mercury, causing it to precess. So, when observations of Mercury's orbit matched Einstein's predictions, it was a major victory for the theory of general relativity. It showed that gravity does more than just pull objects together, it changes the very shape of their paths through space. The perihelion precession of Mercury thus revolutionized our understanding of gravity's impact on orbits. And finally, at number 1, we have the Global Positioning System, or GPS. This ingenious system, a constellation of 24 satellites orbiting Earth, is a constant real-time test of Einstein's theories. It's not just about getting from point A to point B. The GPS in its very operation tests two key aspects of Einstein's theories: time dilation and the bending of light by gravity. Let's talk about time dilation first. According to Einstein's theory of relativity, time moves slower the closer you are to a massive object. So, a clock on a GPS satellite, higher up and away from the Earth's gravity, ticks faster than a clock on Earth's surface. If we didn't account for this time dilation effect, GPS coordinates would drift and be inaccurate within minutes. To keep things precise, the GPS system corrects for this effect, verifying Einstein's predictions every second of every day. Next, we have the bending of light by gravity. Einstein's general theory of relativity predicts that gravity can bend the path of light. GPS signals, which are essentially light, have to pass through Earth's gravitational field to reach us. This causes the signals to curve slightly, altering their path. GPS technology compensates for this effect to ensure accuracy, another nod to Einstein's genius. Now, what do these results mean? They show that Einstein's theories are not just abstract concepts but tangible realities that influence our everyday lives. They dictate how we navigate our world, quite literally. Without Einstein's theories and the tests that prove their accuracy, our GPS systems would be useless, and we'd be left wandering. The GPS, hence, stands as the most significant test of Einstein's theories, impacting our daily lives in ways we may not even realize. It's an everyday reminder of how space, time, and gravity intertwine, and how our understanding of these fundamental aspects of the universe continue to shape our world. So, there you have it. The top 10 space-based tests that have confirmed Einstein's theories. From Gravity Probe A, which validated the time dilation effects of gravity, to the Global Positioning System, which couldn't function without accounting for general relativity, these tests have provided solid proof of Einstein's groundbreaking theories. Each test, from the 10th to the 1st, has been a stepping stone, building on the last, and reaching towards a greater understanding of our universe. Remember the Cassini spacecraft? It used radio signals to confirm the warping of space by gravity, a key prediction of general relativity. Then there was the Pound-Rebka experiment, which gave us the first proof of gravitational redshift, a phenomenon that Einstein predicted in his theory. Gravity Probe B, with its gyroscope spinning in space, checked for the frame-dragging effect. And let's not forget about LIGO, the Laser Interferometer Gravitational Wave Observatory that detected gravitational waves, providing further evidence for Einstein's theories. The Hafele-Keating experiment and Eddington's solar eclipse expedition, each in its unique way, validated the time dilation effects and the bending of light by gravity. The Shapiro time delay and the Perihelion precession of Mercury further underlined the accuracy of Einstein's theories by demonstrating the impact of gravity on the orbit of planets and satellites. And finally, the Global Positioning System, a tool we use daily, wouldn't be nearly as precise without the adjustments made for the effects of gravity on time as predicted by Einstein. These tests have not only confirmed Einstein's theories, but have also enriched our knowledge about the universe. They've helped us understand how gravity affects time and space, and how the universe itself is shaped by these fundamental forces. They've shown us that light too is subject to the laws of gravity. These tests not only prove the genius of Einstein's theories but also continually shape our understanding of the universe. They remind us of the beauty and complexity of our cosmos and of our ongoing journey to understand it. In conclusion, reaching the edge of our voyage through Einstein's cosmos, we're eager to hear your thoughts. What intrigued you the most? Could it the time distortion effects of Gravity Probe A, or the validation of space warping by the Cassini spacecraft, or maybe the discovery of gravitational waves by LIGO captivated you? Or are you still in awe of the GPS we use daily as closely linked to Einstein's theories? We invite you to express your opinions in the comments section. If you've learned something new from this video, we'd appreciate your like. Don't forget to click the subscribe button and the bell icon to stay updated with the more fascinating explorations into the cosmos. We're preparing more thrilling content for you, delving deep into the wonders of our universe and the revolutionary theories that aid our understanding. Remember, knowledge grows when shared. So if today's video has added something new to your knowledge or has aroused your curiosity about our universe's mysteries, don't hesitate to share it with your friends and family. Let's keep learning and discovering together. Until our next cosmic journey, keep your eyes on the stars.